science. And this summer, I had the great opportunity to work with the team at TU Munich. I worked with Alexander Brechner and SNCP. And our research project broadly looks at a causal analysis or causal inference as a form of feature selection, and whether we can gain better understanding about the models and better predictions using causal feature selection. Okay, so why should we predict UAV crashes? Like as UAVs become more ubiquitous, we're gonna see that there's gonna be a lot of problems if we are not able to predict UAV crashes. So, for example, there have been cases that there have been documented cases such as this one in which UAVs can propagate or can generate habitat loss for endangered species. So, for example, this article in the LA Times that says a generation of seabirds was wiped out by a drone in Orange County. Scientists fear for their future. So, and then there's other parts such as if UAV crashes, then that can induce a lot of monetary loss or a lot of wasted time. So, for example, if NASA is developing a drone and it's flying it out for a space mission and it crashes, then it's going to be a lot of taxpayers' money that goes to waste, and also a lot of time from like engineers and everyone in the team. And then like it's more of a joke, but in reality, it's well might happen, but it's more of this like as UAVs become more ubiquitous, we don't want them to like start falling from the sky, and it's going to be like this chicken little scenario where the sky is falling. Yeah, and then why causal feature selection? So as you all know, and you've all probably heard before, correlation doesn't equal causation. And typically what happens in machine learning models is that they're really, really good at finding patterns within the data, but a lot of times those patterns are just like correlations between variables. That's not necessarily that they can find the causal effect, like the cause and effect chain within the data. And in the end, it's easier for us humans to have more inferences to like that cause and effect relationship. And like that goes to the second point of it helps us have a better understanding of the predictions we're making. So for example, I think that a lot of the like one case that all the students are pretty familiar with is for example like the test. Are we able to predict our test score? And like a correlation might be how early you go to the testing center, but then that doesn't really mean that there's like a causal effect between you getting early to the classroom to take the test and you getting a good grade. But there's more of a causal effect in like how much did you sleep last night, how much did you study, are there other things going on in your life, and then using causal feature selection over from giving us better insights and better intuitions as like why predictions are being made and why is that the prediction that the model made. It's going to help us reduce like a possible combinatorial space of UAV initial parameter configurations, which is what we're focusing on in this research. We're looking at the initial parameter configurations of a drone and then using those to predict whether a UAV will crash. And there are many ways that have been proposed in literature to get some causal inferences, like why things happened. One of them, for example, is a fault tree analysis. Then, however, we are focusing on using causal graphs. One of the reasons is that causal graphs allow us to just infer that causal, like cause-effect relationships from the data without necessarily having any domain expertise to create those other models. And in these, here what I'm showing is the Markov blanket. And the Markov blanket is just a set of nodes that are close to the target node. And the target node in this case is this Y red node. And this Markov blanket in the causal graph, well, sorry, first of all, like the intention behind a causal graph is you have a set of nodes and then you have edges. And let's say you have, in this example, you have node X1 has an edge to Y, and that means that there's a causal link between those two nodes. And then we're focusing in the children, which are the direct effects of Y, and then the spouses, which are direct causes of the direct effect. And this is basically the workflow that we followed throughout the summer. It's not perfectly linear. It's just like a really nice abstraction. We had to do a lot of iterations because one of the problems that we have with the data is that there's really no way to detect crashes. And even like in literature, we weren't really able to find any like proposals like this is how you should detect crashes in drones. So we had to generate labels. We had to like find heuristics and come up with ways to like determine crashes just from the data. And then the other thing that followed was doing a causal graph generation, like doing the feature selection from those causal features. And then using those, we went into the prediction analyses. So that's to say that it's not perfectly linear. There are a lot of packages in this kind of like workflow, and there's a lot of iteration between these processes. And that being said, took us to like the preliminary results. There's more nuance to these, but essentially here I'm trying to show that they're like pretty similar prediction like accuracies or F1 scores. However, I believe that later on, and as we do more analysis, there's probably going to be a more of a give and take. It's like the no free lunch like theory that you might get more explainability, but with a little bit of cost in like your prediction accuracy. And then lessons and challenges, as I described before. What like a lot of the challenges were in terms of like the data. There's really no clear and concrete way to identify crashes. And then the other thing is like just like computation time. The algorithm we were using to compute the causal graphs took a long time, so it really required me to go in and write a lot of do quite a bit of parallel programming to speed things up. And yeah, no, I had a great time. It was a really nice way to learn about causality, work with a team in Germany, and get immersed in a domain that I typically wouldn't have been immersed in. Okay, that's my presentation.
All right. Yeah, thank you so much, Ricardo. And I'm sorry, I should have given a brief presentation or a brief introduction for everyone. So Ricardo is working with Dr. Radit Abebe, I believe is how you pronounce his last name, to develop computational frameworks to understand poverty. And then additionally, Ricardo has been working with Dr. Janusz Stepanovits and Himanshu Nima on the integration of different data streams and simulations for the premonition program. So Ricardo, thank you so much for that presentation. We're going to reserve questions for the end, so keep in mind your questions that you may have for Ricardo. Next up, we have Jennifer Fish. She is a sophomore at Vanderbilt, and she's been also doing some dual work on the NSF PIRE project with advisors Dr. Janusz Stepanovits, and then from Germany, Dr. Duck Hai. So Jennifer, are you ready to present?
Sorry, yes, I'm super ready. Thank you for that introduction, Megan. Yes, like she said, I'm Jen. Yeah, and so my first project this summer was through the PIRE program, which stands for Partnerships for International Research and Education. So I was working through the German Aerospace Center at the Institute for Transportation Systems with Dr. Dupley. And the research group was focusing on participatory design and virtual reality, with a focus on cyber physical systems and like human focused approaches. And so they're really trying to integrate the user and the participants into the design and evaluation process for their project, and in order to improve the product's usability and the user's experience. And so my tasks, I started out just by doing some literature research to see what's going on in the current world of VR methods and human-machine interface design. And we're also brainstorming participatory design practices, so involving the user, the research participant, into the design of the product in order to get their feedback and see what makes the most intuitive sense to them. And so my major project was designing a user interface using Unreal Engine that would allow the research participants to customize the human machine interface. So on the right, you can see kind of like a sample of the human machine interface that they're designing. It's kind of an external like light band on an autonomous vehicle that would allow a pedestrian trying to cross the street know that the vehicle sees them and it's safe for them to cross, because you wouldn't have that like eye contact that would traditionally be there if you had like a driver. And so here's a little demonstration of the UI that I made. the research participant would put on the VR goggles, kind of adjust this exterior band. You can kind of see it right here. See what makes most sense to them with like the frequency of the pulsing, the brightness, the tint, as well as adjust the sounds, the volume, just to meet their preferences. And so that was it for the fire project. And then I was also working under Professor Abhishek Dubey, and he's was working on modeling transportation scenarios using a virtual simulator to evaluate their effectiveness under a variety of environmental and traffic conditions. So I used a simulator called Carla, which allows the user to control the traffic, the pedestrian behaviors, the weathers, the sensors, all kinds of parameters. And we integrate it with Scenic, which is this programming languages that allows you to program different configurations and scenarios. You'll like changing the parameters, changing the number of simulation runs to figure out which parameters lead to a larger degradation or performance degradation of the autonomous vehicle. And then here's a little demonstration of the Carla and Scenic integration. You can see you can control the other vehicles and your location in the world, and you can control like the weather. So just seeing which parameters lead to more of a risks for the vehicle. And so yeah, that's about it. Overall, I had a really great time this summer. I got to work with a bunch of really smart people. It was a little bit weird at first, like being in two different projects. So I had to kind of like balance the two groups and prioritize my projects for the week. And I learned like there are a lot of people that are a lot smarter than me and that have more experience in the field. So like don't try to do everything myself. Like they're super willing to help me. But there's definitely a pretty steep learning curve for the new platforms that I was using, but ended up being super fulfilling and gained a lot of new familiarity with new platforms and programs. And also I learned a ton about all of the new current research being done in the world of autonomous vehicles, which I think was really cool. So yeah, that's about it. Thank you.
All right, thanks, Jen. Very good on timing. Next up, we have Ben. Ben, are you ready to present?
Yeah.
Okay, perfect. And Ben has been working this summer with Professor Abhishek Dubey.
Yeah. Hey, everyone. So this summer, I worked with Professor Abhishek Dubey and his team, which is the Scope Lab on deep learning with computer vision models. And my research project was based around the passenger counting and tracking convolutional neural network model being tested and trained on CARTA, which is Chattanooga Area Regional Transportation Authority bus videos, but that was for use in Nashville. So before I joined, the evaluation of the pre-trained generic convolutional neural network models on CARTA videos were done, but one of my objectives was to evaluate most of the state-of-the-art models specific to crowd counting on CARTA data. And then based on those results, the second goal was to label and annotate CARTA data with more attributes to train a new network from scratch so that the evaluation results and the new models performance could be compared. So yeah, so my tasks included downloading the video from the CARTA server using the remote desktop protocol and then extracting out the images from the videos at a certain frame rate using Python scripts. Then the next task was to annotate the images for ground truth data for testing purpose. So the images were annotated as per the specific model's needs using CVAT, which is an annotation tool. And then a density map was generated from the image using Gaussian convolution in MATLAB. And the reason behind using density maps was that because it takes into account the spatial distribution of the people as well. And then the specific crowd counting models were trained on two publicly available crowd counting datasets on Google Colab on the NVIDIA KT GPU. And then the prediction and the ground truth values were evaluated, and the results were compared. So the model results were then compared using the mean absolute errors and the mean squared error values for the number of people detected by the models. So as you can see, some of them perform well, but based on the overall results, a model trained on Carter data itself could be better. So the next part of my training was labeling, and for that purpose, the Carta videos were extracted and the images were annotated using more attributes to uh, uh, distinguish the recognition features among the passengers. And then a good amount of time was also spent on discussing the guidelines to be set for annotation in the uh, model. So that was done in collaboration with Dr. Lasga's team at the University of Houston. And since then, around 1,500 images have been annotated, including both point and box annotations for the new network. So yeah, that was it. So the challenges that I faced this summer was basically I had minimal experience on Python, deep learning, as well as computer vision. So the prep work was a lot in the beginning, and then adjusting to the remote setting was a little bit difficult as well. But then the positives were that I got a lot of experience with convolutional neural network modeling, and then Python, MATLAB, a lot of new languages, as well as a lot of new packages as well. And then also Professor Dubey and his team was great during the whole project. So I got a great team experience as well as the lecture series for ISIS were pretty great. And some of the lessons that I learned were that continuous feedback is really important to stay up to date, because yeah, that was one thing that I learned. And the other thing was that experimenting with the code can be really beneficial to find better and efficient methods. So yeah, I think those were the things that I learned. Thank you.
Awesome. Thank you, Ben. That was great on timing. Before we move on, are there any questions for our first three presenters? Okay, if not,
I've got a question.
Yeah, go ahead,
Yeah,
Daniel.
for the last presenter, how long did it take you to train these? I mean, to label these data sets?
Well, the most important part was getting the guidelines to label the data set. So that was the longest, but then, selecting attributes and then the IDs of the same people on different panes of the videos were maybe around 4 to 5 weeks. Yeah.
So I'm confused. How many images did you label in that time? I'm just curious, like for each image, I mean, are you manually doing it? And if so, like how long per image did it take you once you were up to speed and comfortable with it?
Around, I mean, it depends on the number of attributes, but we used 8 attributes. So and a single image would take about like 4 or 5 minutes, maybe, depending on the number of people.
Okay, thanks.
Yep.
All right. Okay, looks like there's no other questions. So Hunter, we're going to move on to you. And this summer, Hunter has been working with Dr. Abhishek Dubey and Dr. Ayan Mukhopadhyay. Hope I said your last name right, probably not, so apologies on that. But Hunter, are you ready to present?
Yes, I am. Thank you for the introduction.
Yeah, of course.
So my name is Hunter Baxter. I'm a math and computer science major at Vanderbilt, and I had the opportunity of working under Dr. Abhishek Dubey and Dr. Syed Mohsen Bezirzad. And so this summer I worked on 2 projects, the first being a data pipeline and the second being a feature selection module. Okay, so before I go into my projects, I want to quickly introduce emergency response management. The big challenge for the Tennessee Department of Transportation and really any other first responders is that they need to manage incidents spread over a large geographic area with limited resources. The faster an incident is cleared, the less congestion and the better the recovery. To reach this goal, we collected a large amount of data over a large geographical area over a large period of time. The size of this data poses some challenges. And to make better decisions regarding emergency response, it is necessary to predict where incidents will occur. So with these projects, I was working primarily with 4 data sets: the Tennessee Department of Transportation automobile crash data, INRIX traffic and road segment data, and WeatherBit weather data. My responsibilities regarding this data were partially to clean and prepare this data so it was actually usable. For example, I was responsible for documenting and reporting the problems with the Tennessee Department of Transportation automobile crash data to the Tennessee Department of Transportation. So for example, an issue that some of the data had was that the latitude and longitudes were either switched or had negative values, were missing, or were just unusable. So for example, on the right is the before and after of the cleaning process. And the table below, it actually is a screenshot from the report I sent the Tennessee Department of Transportation. Next is my first project, which is the data pipeline. And the main challenge after you collect data from the data source is making a singular data set that can be used in a machine learning model. So since the data was in total around a terabyte of size, this poses some challenges that make traditional methods not viable. So with taking memory size into consideration, we deployed this with using Amazon Athena. And this is an SQL engine using Precito. So after these data sets were combined, we then use Apache Spark to aggregate historical features for each road segment. Next, my next project was the feature selection module. So there are a few reasons why feature selection is important. The first being that to even open this whole joint data set, it required 128 gigabytes of RAM, which isn't feasible for most computers. So when unnecessary features are removed, there's less data, less memory needed to handle the data. And then with a smaller data set, it's much faster to train. And this is important when you want to experiment with a lot of different models to find what's best. And the third being that some data has noise, meaning that there are some features that have little to no use in prediction, and that including these features can actually hurt a model's performance. And 4, a model with fewer features could potentially be more parsimonious, meaning that there is less complexity and better performance. And this is very useful for actually interpreting a model to first responders. So to do this feature selection, we are using an algorithm called maximum relevance, minimum redundancy. And this is a iterative greedy algorithm that selects features with the most relevance with the response variable, but with the least redundancy with already selected features. And to evaluate the effectiveness of this method, we'll be comparing this to regularized machine learning models, and then machine learning models without input that has been using machine learning models that don't have, I guess, reduced features size. And then so even if the performance is the exact same after this feature selection is done, it would be considered successful because it's less computationally intensive. So just to comment on my internship, it went really well because I developed practical solutions for an industry partner, and I learned tools for deployable solutions to big data problems. And I think the only challenge I really faced was that I had to learn how to eat a healthy lunch daily and not just eat a Cliff Bar over the keyboard while working. Because in the long run, taking a 25-minute break to have a healthy lunch was better for sustained concentration. And if I had to choose one out of the many lessons I learned, it would be that it's better to work slower and build a better solution than to work faster and need to debug or refactor later. And to conclude, there is intent to publish methodology and results of feature selection module in the IEEE Big Data 2021 conference. And I'm really happy that I will be continuing research in the fall of 2021 semester for research credit hours. And thank you for listening to me today.
All right, thank you, Hunter. Thanks for the work-life balance insight. That was great. All right, next we have Eva. Eva, are you on and ready to present?
Yes, let me share my screen.
Yeah, and then Eva has been working with Dr. Daniel Balasubramanian. So whenever you are ready.
Yeah, thanks Regan for introducing me. And this summer I've worked on 2 languages or frameworks, which are Formula and P language. And special thanks to my mentor, Daniel, for introducing me to these interesting topics and offering me guidance all the way. All right, so let me give you a little bit intro of formula in P language. So first, what is formula? Formula is a language and framework for specifying domain-specific languages and checking properties of those specifications, and it aims to provide efficient reasoning and compilation of input programs, as well as symbolic model generation. And formula specifications are written as strongly typed open world logic programs. They're highly decorative and can express rich synthesis and verification problems. It enables model generation by efficient symbolic execution of logic programs into constraints. Maybe this doesn't make much sense to you right now, but hopefully I'll give an example later, and maybe you get an idea of what it does by that time. And what is P? P is a domain-specific language for modeling, specifying, and testing distributed systems. And the original P compiler was implemented using formula. And what I did this summer was I expanded a set of example formula programs, created tutorials, tested new features, and developed a wiki page with documentation. And I also learned about the domain-specific language P and helped identify changes to the P language that were made since the initial P compiler was migrated from formula to a standalone compiler. All right, so here's an example formula program. So what we're trying to do here is we're trying to create two domains, regular trees and algebra trees. And the picture on the left is for the regular trees, and it is done in 3 steps. By adding conformance constraints to each step. And for the algebra trees domain on the bottom, and you can see from the right picture on the right side, it is done by using the data constructor node, which has 3 arguments: the dat, which is an integer, and also the left child and the right child. So that way we can define a domain algebra trees. And you may notice that these 2 domains have the similar structures. And you might be wondering if we can transform them to each other. So that brings us to another thing that formula can do, which is transform. It's a little bit long, but don't worry about it. Basically, this transformation is to like transform the nodes to its corresponding vertex, and using the parent-child relation to define the direction of an edge. And the picture on the right is how we construct the path data. And the root case and the left child case is relatively simple, but the right child case involves the another data constructor ID max, which defines a max ID for a path. And the next picture shows how we define the max ID of a path. And the case 1 deals with the end node case, and the case 2 is defined recursively, either by left child or right child. All right. So this example may be a little bit heavy with mathematics. So here's a more pleasant example of P language. So so what this program does is actually what this animation shows. I assume all of you know how to play ping pong. So we have a client, the black cat, and also a server, the white cat, and they are just playing ping pong. Yeah, as you can see. And if you get stuck, like the white cat, and the event failure happens, we have a way of cleanly terminate the program, which is raise halt. All right, so yeah, this is what it does. All right, so thank you for listening.
All right. Thank you so much, Ibe. I enjoyed the little video presentation. That was good. So thank you for sharing.
Thanks.
Yeah, thanks. Next up, we have David and Adi. They also worked with Dr. Balasubramanian, and I believe that they will be co-presenting. Feel free to correct me if I'm wrong there. And whenever you guys are ready, you have the floor.
Awesome. All right, let me get started. Hi, everyone. My name is David, and I worked with Audie, and we worked for our principal investigator, Dr. Daniel Balasubramanian. And today we're going to talk about the open data collection framework for improving the neighborhood safety around Nashville. So let's get into it. So our project's big picture was, how do we improve the neighborhoods using technologies such as cameras, phones, databases, machine learning, and computer vision? And there were some social issues that came up with it, such as privacy, data retention, ownership, trust, and surveillance issues. So as you can see the diagram on the right, we have a database that's maintained by the community, and the police can request to access the data, and the data unloaded through computer vision camera capturing like the license plates or the lost pet, and the community members get to contribute and also use that database very easily through an app. So we're gonna look at some demos before we get into more details. Sorry, sorry, my bad. I'm gonna unshare and share the sound one more time. Sorry about that.
Yeah, no worries.
Hopefully the sound works.
Just have a break, go for a walk. Oh yeah, I should go for a walk. What's wrong, friend?
I lost my dog.
Really?
Yeah.
Okay, if I find it, I'll upload the open data app and you'll see it.
Okay, thank you.
All right. Wait, this is dog. All right, let me take a picture of it first. All right, let me get onto the open data app, animal dashboard, and I'm gonna unload the data. All right, it's a dog. It's a boxer, probably. I'm not sure, but it's brown, and it's at Vanderbilt. Let me get my location, and I'll upload the picture as well. Let me get it from the library. It's right here. Awesome, man. Upload. All right, I hope my friend sees it.
Oh wait, I got an email that says my lost dog's been found.
Now you can go through the data, and if you find one, you can see exactly the location where it was reported from.
Hey, Biscuit.
So yeah, that's the demo of it. And there's another demo of license detection app. So the user has to put in some information before detecting a license, such as the company, the model, the color, and approximate neighborhood where the user is detecting the license from. And we just didn't want to detect any random car, so I just try to detect a language. So we can go back to the dashboard, and it will be uploaded right here. Same information, BMW X3 and the license plate as well with exact date. And if we click it, we can see exactly where the data was unloaded from as well. So that's a demo of how two different apps can be used. Now I'm going to talk about the front-end side where I work. So I use Ionic React for the dashboard app and React Native for the license detection app. And the languages I used were TypeScript, JavaScript, HTML, CSS. So I got exposed to all different types of language. So And those were cross-platform, so I could run the app on iOS and Android devices very easily. And it was very easy to handle like data retrieval using those data, such as that. And the challenge that I faced was incorporating front end with the back end, which Audis can explain more about. It was my first time trying to get user registration, login process, and retrieving and using all the data. But once I got hang of it, I was able to use it really well. The lesson was to be persistent with an open mindset. I got frustrated quite a lot of times throughout the internship because of the coding, but whenever I had this frustration, I took a break and came back to the problem with open mindset, and it really helped me to solve the problem well. And I cannot appreciate enough of how much I enjoyed working with Audi and Dr. Velas Romanian. It was awesome to help and support each other a lot and push each other to work hard every single day. And these are just brief UI designs, this homepage, profile page, we have dashboard page, and we also have query page where you can put one or more parameters to search up a data. And we try to make the design easiest, very simple so that user can use it easily. Now I'm going to hand it over to Audie to talk more about the backend side.
Hey, so I'm Ali Bajpai. I work on the backend side for this whole project. The backend, that's the link for all the code we wrote on the backend. This is the thing that integrates with David's front end, and it's really interesting the way it just spanned the project. So we used we used JavaScript for the backend, and we used GraphQL, Express, MongoDB for the core components, and then we used Nginx for the reverse proxy. There is a nice image showing the architecture of it later, which we'll go into in a second. Other than that, so before I talk about these features, we also use some secondary stuff. So like there's a Swift storage cluster at Vanderbilt that's used for storing images. So that was an API that was really interesting to work with because it wasn't really well documented. So I kind of had to like figure it out by just trying a bunch of stuff out and then writing functions that would mimic the same thing instead of like using some prepackaged library or something like that. Then there was this one other interesting thing that we needed was that, so like in the video, as you saw that like David and his friend were in the same neighborhood where they were able to access the lost pet. Now, we don't want this to happen for like a person to have access to all the pets that are being created. You want to restrict them to their own neighborhood or something. So for that, we sometimes need to detect the person's nearest neighborhood. So this was a nice challenge. And the way we did that is by using something called the Haversine geolocation formula, which calculates the distance between two, like a pair of coordinates, right? So latitude and longitude. So by that, we were able to get the nearest neighborhood from any given location on Earth, right? So that was quite interesting. And the other thing is that while we didn't have access to real data or animals, as you saw in the video while testing, we had to create a lot of fake data just to facilitate testing. So that was interesting, but it also had its own set of challenges. Like, for example, if you're generating fake GPS coordinates using some library, random coordinates, there's a big chance that they won't be where you want them to be. Like, for example, we would want to restrict them to Nashville or something, but in the first few runs of this, we had a lot of cars and animals just right in the middle of the ocean. So for that, we kind of had to restrict, like start off with some base coordinates or like Vanderbilts and then do some math.random stuff. So like it just varies a little bit, but not so much that it ends up in being like Georgia or something. Then a few design choices that I can talk about for the backend, since there's no nice video or something, unless y'all are interested in seeing like a video of an ISIS server that's running the code, is that we didn't use a REST API here because GraphQL made more sense. The reason GraphQL made more sense here is that GraphQL allows you to simply return objects and model the object type and stuff like that. So we have like an animal type, we have a vehicle type, we have a neighborhood type, a user type. So it made it really easy to just use GraphQL for this because it would do the heavy lifting for us. We just had to give it the data, and it just serves as a nice layer between the client and the database. The hot list feature that we just saw, where like a person can register like a partial description of their animal, was also really nice, and we just did really recently. So a user can register like a partial description of their animal or vehicle, and then whenever a vehicle or animal is created by anyone which matches that, then the user will automatically get an email with the details of the animal and vehicle that was just added to the database. Yeah, this is really nice because it allows people to have like matches like just sitting there in the background whenever their pet is hit or if their vehicle is hit or something, and coupled with the license detection thing, this can be really useful for just having something so like a safety feature for your own pets and cars. The third thing is that the choice of the database, because like before this, I had usually worked with like SQL databases, so like Postgres or MySQL. But for here, MongoDB was quite interesting to work with. It's much more free, and there's not much. Hey David, can we move to the next slide? I think it will be useful to, yeah. So that's sort of the architecture. The reason MongoDB was useful to work with is that if you're linking to models or something, then we don't need to do like chain joins that we do in SQL. We can just link them using the object ID, which made sense because we're linking the user and the neighborhood and all of that. But yeah, that's the architecture. We have the Nginx reverse proxy that directly goes to Express that deals with the Swift images and stuff, and Sentry, which we use for error handling. And then GraphQL is the only thing connected to MongoDB. So we have some security in knowing that like the database is not accessed from anywhere else. And the client basically deals with the front end other than the emails they get. So pretty simple, honestly. Now we have some example of like queries and stuff. Yeah, thank you, David. So you can see this query just lists out all the neighborhoods, although there's some in the other tabs that are not open. And the data format exactly, the return format exactly mimics the sort of data that we have there. So I think that's pretty useful for the front-end person to know the format of the data they're getting back is the same as the query they're sending, which I think makes it easy for development and integration. Next slide, David. And then we also made a website, normal website using Hugo, which is an engine to just generate static websites. We used a nice theme that had like that was trying to get us to buy Apple watches or something. I think that was a demo website. And then David fitted it out to be for us, and it turned out really well, and it looks really nice. So that was good. And yeah, that's pretty much it. We had a fun time working together. And there's still so much to do, right? Like, as I mentioned, we're using fake data. So now this step would be to actually deploy models and cameras and stuff to get real data that does that. So yeah, it's pretty fun. And there's Dr. Balasubramanian's email if you wanted to get involved.
All right, thank you two so much. That was a very creative presentation. I enjoyed watching and listening. Before we move on to the next presenters, I'm going to take a brief pause to see if there are any questions for our previous 4 presenters or the 3 before that. Again, we had David, Adi, Eva, and Hunter who just presented. So any questions for those 4 or the 3 students before them? All right. If not, I believe our next presenters are also co-presenting. We have Maya and Gracie. Maya and Gracie, whenever you guys are ready, you can pull up. Oh, and you're in the same room. That's great. Yeah, so Maya and Gracie did some of their work at the VU ISIS building. Again, we've had more opportunities this summer for collaboration. They worked with Dan Work, I believe, and I am interested in seeing what they have.
Sorry, it seems I need to change some kind of privacy setting to screen share.
Okay.
Oh, yeah. Okay, that's a good idea.
Yeah, no worries. And in the meantime, again, oh, nope. Looks like, okay. Perfect. Okay, you got it figured out. Yes. All right. Thank you so much. Whenever you guys are ready, the floor is yours.
Okay, so hello everyone. My name is Maya.
And I'm Gracie.
And we worked in Professor Daniel Work's lab with our mentor, Matt. I think he's here, so shout out to Matt. Yeah, so just to start out with some background, like information and context on the larger project that we're working for, so that when we talk about what we did specifically, it makes a little bit more sense. So the project that we're working on is part of a larger multi-university research group that works on a number of projects related to autonomous vehicles, including development of like simulation, vehicle simulation technology, development of like control algorithms, as well as infrastructure, highway infrastructure for traffic data collection. So furthermore, more specifically to like what we're doing, the team has been developing a multitude of vehicle control algorithms to be tested on I-24 right here in Nashville or in Tennessee, based on data collected from 44 drives along the stretch of roadway from March to May this year, many of which were conducted by Gracie twice up and down this roadway. Oops. So again, this will all be coming together in a little over a week from now, in the first week of August. The project is doing a test with 4 autonomously controlled vehicles and 7 manually driven cars along that same stretch of roadway. And the purpose of this experiment is to test the various velocity controllers on a railroad, as well as measure their effects on fuel consumption along the roadway in various scenarios. So as you can see on the slide, we have like the 2 different scenarios that the cars will be driving in, like a single lane and multi-lane scenario. So this is some dash cam footage from one of the drives. And one thing to note is that usually it also has the GPS location. So we'll get into it a little bit more later, but the cars are obviously, decked out with a bunch of sensors and whatnot. So now actually moving on to the work that Gracie and I did over this past summer and actually are continuing to do for the next 2 weeks, but we couldn't make it to the other presentation date. So our work was pretty varied with both logistical and technical aspects. On the logistical side, we did a few different things. We've been involved in recruiting and training drivers for the upcoming experiment and helping to figure out details such as like hotel booking for all the people coming to Nashville, as well as submitting IRB documentation to grant us exemption from regulations for experiments involving human subjects. And we also have and are continuing to do practice drives both along the I-24 corridor and at the Nashville Fairgrounds Speedway, which we're actually going to today, which is a lot of fun. And you can see the picture at the top there is from the Speedway. So yeah, also it's worth mentioning maybe that we're both going to be driving cars in the experiment, which is exciting.
Yeah. Okay, so for more of the technical preparation that we did to get ready for this experiment is that all of the vehicles that we're using, some of these are rental cars that we're actually picking up next Monday. And then we have one lab car that has been with us since this past year. And then we have a couple cars from UC Berkeley that are either here or on their way, and then a car from Arizona. So for each of these cars, we use Comma AI hardware to instrument them to collect CAN bus data from the vehicle. So the demonstration of that is shown below. So essentially the Raspberry Pi is the computer that actually collects the data and then uploads it online, and that comes from the Black Panda, which is then connected to the car through the car harness and so on. So from that data, we used a Python package called Strim to analyze that. And this is a package that was developed by some of our fellow Circles researchers, and it provides APIs to the user interface in order to take this data in a more like readable and just analyzes it so that we can see traffic patterns and then energy smoothing eventually. So one other thing that we did this summer was shown in the picture that's on the right of the screen is that we tested advanced GPS devices to calculate the error on the I-24 motion camera network. So this camera network is installed by TDOT, and like Maya had mentioned in the last slides, that little test bed where we drive is where these cameras are located. So we currently only have a small portion of the test bed covered with these, but come next year, they will be extending this camera network to cover even more of our test bed. So yeah, these GPS devices, it has a magnetic piece, and that's what's shown above, and that attaches to the top of the car. And then those wires run down through the car through a little computer, and then it plugs into a laptop so that when we tested this, someone was driving the car and then someone else was in the back of the car with the laptop using this application just to make sure the data was being recorded correctly and that everything looked good from that end. So this slide is just an example. So this top picture is what the CAN bus data looks like when it comes off the car. And then each of those message IDs on the left represent something different. So for instance, message ID 180 represents the speed of the car. And then this bottom picture is just an example of something that we can use Strim to replicate these tables. So every time we use Strim, the first thing that we do is we get a count of all the data, which is what, and then it outputs that graph below. So that just makes sure that we can tell if all the data was recorded correctly and there's not any like missing pieces. And then another useful thing that Strim does is that it allows us to visualize the GPS data that we've collected from the car. So it'll output it on a map like this, and we're able to trim it just to represent certain aspects of the drive or just display it all together as shown below. So yeah, a lot of the research that we have been doing this summer obviously is important for the experiments that we're having starting next week, but then it also is setting up a baseline for the experiment that we're going to be running next summer, which will be a 100-car traffic smoothing experiment. And like I mentioned before, this involves the extension of the I-24 highway sensing infrastructure, that some of which is already in place and more of it is going to be installed later. And then, yeah, we'll still be testing the various custom velocity controllers that this summer will be used in the 4 non-manually driven cars. And then next summer we'll have even more of these vehicles using those software. So yeah, some of the challenges and lessons that Maya and I have encountered this summer is one challenge that was bigger than we thought was just planning all the logistical aspects to this experiment. So when we have our colleagues traveling in, and it's just been an issue trying to book down, for instance, a rental space for our staging area, since it's all the way out on Sam Ridley Parkway in Smyrna. We've been trying to find a good area to have air conditioning, outlets, internet, etc., so that we're able to work closer to where we will be having the cars leave from. Additionally, a more technical challenge that we've faced is getting our Raspberry Pi computers connected to battery packs so that it will automatically upload our data to Cyverse that it collects, rather than us having to go down to the cars every so often and bring the Raspberry Pi up to the office space to then upload it manually. And on the first note, additionally, just taking our ideas from theory into execution, especially when it involves having 15 or 20 researchers come and visit Vanderbilt and work in our office. It's taken a lot of planning to make sure that we're set up to host that many people and that everyone will be able to do their work in our office. And yeah, one last thing is just any issues that we've had now with setting up software or making sure that all of our cars are properly collecting data, is that if we have any issues now, we really have to figure out why those are happening rather than just temporarily fixing it, because we'll be using all the same software in the upcoming 100-car experiment. So yeah, that was all we had. If you guys have any questions or anything, let us know.
All right, thank you guys. Really engaging presentation once again. We're doing great on time. You guys were under time, so if there's any questions for Maya and Gracie, we can take one of those really quickly right now.
What assumptions do you make on the other drivers?
Like as in like the other cars on the roadway?
Right.
Well, essentially, how this experiment is going to work is the 11 cars are going to be collecting CAN data. So then what we're going to do with that is compare the cars that are upstream of our 4 like custom velocity controlled cars to the cars that are progressively downstream. So I guess to answer your question, we're not overly comparing them to like regular drivers that are not part of our experiment, and we're mostly just comparing the upstream and downstream vehicles.
I suppose part of the idea is to see how the autonomous vehicles impact the like fuel consumption theoretically on those, like external cars, but obviously there's no way to, see that. So then our own censored up vehicles will be used for that.
Okay, thanks.
All right, awesome. Thanks, you two. Next up, we have Carmen. Carmen, whenever you are ready, you can get set up here. And then Carmen has been working with Dr. Taylor Johnson on the neural network and machine learning verification project.
Hi, thank you, Reagan. Can you see my screen?
I can, yes.
Okay, so the project I worked on was the GTSRB neural network and verification. And GTSRB is like a German road sign data set that has like images of road signs as shown here as an example. And it has like associated labels that essentially tell you what type of road sign it is. So the purpose of this neural network is for image classification, which is a technique used to essentially give a input image to a neural network, and it will tell you like what label it's associated with. So the purpose of a neural network for people that are that don't know what it is it's essentially a function that takes in like a input or set of inputs, and then it would map that input to a output label or class. And in this specific data set, there were about 39,000 images for the training data, and there were 43 output classes. So each image is associated with one class, and the goal is to find out like what image, without having the knowledge of what class it is, would be associated to which label. And so the implementation of the neural network was done in Python with Keras and TensorFlow. And this is sort of like the structure of the neural network that so the main issue that I had was like figuring out like which structure would work the best in order to have the highest accuracy. And the way you determine accuracy in neural networks is by using the test data, and um, that you run the test data into the neural network, and then you figure out like what the output is and then compare it with the expected output. Now we don't do this with just the training data because there's the chance that the neural network may be overfitted to just the training data, which would skew the results. So generally the testing data is like separate from the training. And so based on the results, we saw that the training time was about like 90 minutes for the neural network for the 39,000 images. And the accuracy that we achieved was about 95%. And like a lot of the struggle with designing the network was just like figuring out like which layer types are compatible with like uh, the other tools that the lab uses, and also just to maximize the amount of accuracy we have on the data. And there are some like verification applications that neural networks that this specific neural network is used for. So the main idea about verification is to measure sort of the robustness level of a network. And what that means is that so you can do that using our adversarial perturbations, which is essentially like introducing a level of noise to the image and see if it classifies the image correctly or incorrectly. And like there are like a lot of tools, and the tool that our lab uses is called the NNV tool. And just based on this example, like it says like it's adversarial perturbations, but it doesn't even have to be like a actual attack that someone does to an image. It could just be like a stain on a road sign or something. So this image example is taken from a paper that showed that if a stop sign had like a little bit of stain or shadows like that, it may be misclassified as a speed limit like I think 25 or 35 sign. And that would be a pretty big issue, because imagine if you have a self-driving car and it sees like the stop sign and your neural network predicts it as a speed limit sign, then it would just like skip the stop sign and keep going. So that could be a very detrimental issue. So that's why we're interested in looking at the verification applications. And the main issue I had with this portion of the project was that it would take about 40 to 50 minutes for each image to go through the tool and get the reachability analysis out of it. And that would just take a long time for all the images, because if it works for one image, it doesn't necessarily mean that it would work for every image. And so there are other libraries such as Fullbox that could be used to find some adversarial perturbations and see how those play out with the network and measure the robustness that way. That's it. Thank you so much.
All right. Thank you so much, Carmen. That was a great presentation. Next up, we have Rahul. So Rahul, whenever you are ready.
Okay, I'll just go ahead and get started then.
Okay, and then yeah, for everyone who's listening, Rahul worked with Professor Andy Gokhale. So
Okay, so I work with Professor Gokhale on one of the problems he's looking into, which is DDoS detection in software-defined networks. So to define some terms, a software-defined network is a network that uses software to control network infrastructure and traffic flow, as opposed to a traditional network, which uses hardware such as routers and switches. So software-defined network is much more flexible in that sense. And a DDoS attack is a distributed denial of service attack, an attack where a target is overwhelmed by network traffic from multiple sources, which causes disruption in the target's network services, causing them to be unable to use any services that connect to the network. So the problem statement I was working with for the summer is, given traffic flow information in an SDN, how can we detect a DDoS attack on the network? And for the summer, I designed 2 approaches based on some papers I've read. And the first one is an entropy-based approach, where I used a modified Shannon entropy formula to calculate the network's current entropy using packet flow headers such as source and destination IP and packet content and so on. Packet content as in length and then what type of packet. And I used the calculated entropy to determine if the network is under attack based on anomalies in the entropy. So if the average window for an entropy is around 10 for a 10-minute window, and the entropy suddenly drops to 1 or spikes to 20, then I detect those as DDoS attacks. And the second approach I tested was the machine learning approach, where I used the traffic flow information such as the packet header information from a packet type, a packet length, time to live, and I used that information as a feature vector, and I applied a machine learning model to predict the network state, DDoS or no DDoS. And I tested 4 types of models, which are decision tree, naive Bayes classifier, SVM, and random forest. These 4 approach the classification task differently in terms of how the model is actually designed. So I decided to see which one worked the best. And I found that the most performant was the random forest. And the results for the model are that in the entropy method worked well in the testing scenario. And the testing scenario is a basic scenario where I set up a software-defined network with a single virtual switch and n number of hosts, which can vary from 4 to 10 and even 20. And so I found that the entropy method works well in the simple testing scenario, as I managed to detect DDoS attacks during replayed attack scenarios, but was unable to detect the DDoS attacks during the period after an attack has occurred, since the entropy values are still skewed from the DDoS attack. And I found that the machine learning method works well with the data set around 0.9 for F1 precision recall and 100% accuracy, but not well in the testing scenario. And I found out that is because the data set that I used to train the model didn't reflect the actual testing scenario that I wanted to test. So I'm currently collecting more data to work on this, as this is a continuing project. And next steps that I'm working on right now are to create a new data set for the machine learning approach to train the model to accurately detect different types of traffic, and to test both approaches using different network scenarios other than the single switch and number of hosts. And also want to investigate failure cases for the DDoS detection in the case that running the detection software on a centralized SDN controller as opposed to running it on localized virtual switches in the network. Basically a centralized versus distributed approach. And as for the actual internship, some lessons that I learned were to communicate frequently with my mentors so that I could get advice on my thoughts and my plans, just so I can see if I'm on the right track, and to document my thoughts so that I don't forget what my plan is and what I want to do the next day. And some challenges I ran into were the initial learning curve with the tools, since these tools weren't particularly well documented. And in that same regard, I ran into issues with the framework itself, since they weren't really that well documented. Some things that went well were that it was a very educational experience, and I now have a better understanding of the field of software-defined networks. Yeah, that's all. If there's any questions, I'm happy to answer.
All right, thank you so much, Rahul. Before we move on, are there any questions for our last two presenters, Carmen and Rahul? Okay, if not, Olivia Logan will be our next presenter. And she has been working with Dr. Gautam Biswas on one of the open-ended learning projects that she will tell you more about.
Yes, hello. Hi, my name is Olivia. As Regan said, I am a computer science and psychology major. I'm a rising junior at Vanderbilt, and this summer I worked with Professor Biswas in his open-ended learning environments lab, and specifically on his Betty's Brain project. So a little bit about Betty's Brain. This is an online platform used in classrooms for students to learn concepts by teaching them. So it's specifically targeted at 5th and 6th grade students, and I'll try to refer to these students as the user. In the platform, there's two characters. So one is Betty, and this is the student that the user is teaching. And then the second is Mr. Davis. And every now and then, Mr. Davis kind of comes in to give feedback and encouragement to the user. There's also 3 different components to the platform. So the first is the science text. This is where the user will go to kind of learn about the different concepts. So if they are in the climate change module, then they'll go to the science text to read a little bit about different climate change concepts. And then the second part is concept maps. So this is sort of like the main draw of the platform, and it uses this idea of co-activation, which is essentially meaning that if you create links between different concepts, then they'll be associated with each other and you will remember them better. So the student comes in and creates links between concepts in their concept map. And then the third part is quizzes. So they will tell Betty to take a quiz when they feel like their concept map is ready. And then Betty will use that concept map to answer quiz questions. So this system was actually implemented, I would say started around 15 years ago. So it's been around for quite some time. It's been implemented in classrooms, but what we're currently doing is improving the system by adding feedback to it. So as you can see on this slide, here's a couple of screenshots that I took of the application. On the left side, this shows the quiz view. So on the top, you can see quiz questions that Betty answered, and it's all related to the concept map. So if she got something correct, that means that the links are correct. Whereas if she doesn't know something, that means that the student is probably missing that concept in their concept map, and they don't have the right links yet. And then on the right side, you can see that Mr. Davis has kind of popped up and he sees that the concept map isn't going very well. So he might, try to give the user a hint or two about their concept map. So in terms of my work this summer, we are currently, as I said, improving the system by adding feedback to it. So I first came in and kind of just tested the platform. Specifically, I tested the climate change module. And I just kind of gave a fresh pair of eyes to the system and, gave ideas about its usability and effectiveness. I also started presenting research papers. So I looked into different learning and memory concepts that I don't have a ton of time to go into, but essentially I'm just kind of researching how to help students who are having difficulty in the system. And then I used that research to share ideas about how to improve the feedback. And then what I've been working more recently on is starting to code behavior trees. So feedback is implemented in the form of conversation trees. So as you can see on the right side of this slide, this is just one very small part of the tree. So this is one level of the read to build coherence feedback, which means if the user is going back and forth between the science textbook and the concept map, but the concepts that they're reading isn't really related to the concepts that they're building in their map, then this will trigger the read to build coherence feedback. So what happens here is that Mr. Davis will probably pop up and start a conversation. So I'm helping code, some of these behavior trees. And then I'm also going to be leading a study, sort of a test run with undergrads in the fall when school starts. So I've been starting to, write procedures and things, setting up eye tracking technology for those. In terms of the lessons and challenges, I'll just start off with what went well. So it was really cool to be able to combine computer science with learning, memory, and education, 3 things that I'm very interested in, and it was awesome to be able to combine it with code. I also loved being able to come up with creative ideas and be able to share them in a way that, my input was really valued. But of course, coming with that is some challenges, just being able to kind of connect the research papers that I was reading in our context and come up with, new ideas came with a learning curve. And then I also learned to take initiative even when not asked to. So this is always just a good idea, and it allowed me to gain more from my experience this summer. So yeah, that's about it. I'm very grateful for the opportunity that I've had, and I've had an awesome experience.
All right. Thank you so much, Olivia. We appreciate your presentation. Great presentation. All right. And then our next 2 presenters, so I believe that they're presenting separately, but both of them worked for under Dr. Jules White. So our first presenter will be Clayton Clay Wright. And whenever he is ready, he can get his slides pulled up, but he and Randy did a lot of collaborative work under Dr. Jules White. So.
Cool. Can you see my screen?
Yes.
Awesome. Hi, guys. I'm Clay Wright. I had the opportunity to work with cyber physical steganography with STL data under Dr. White this summer. So basically an overview of what I was working on is our goal was to develop a system that could identify a 3D printed part by hiding the metadata of that part inside of first an image of the actual part, and then later, once that object is printed, the metadata is actually included inside of the object itself. So then later a consumer, if they wanted to, could identify this part by extracting the information from, let's say, a picture of the object or like something else like that. So some open questions that we're still working through as of now are, 1, how are we going to physically embed the information without compromising the physical properties of the component itself? And also, how are we going to recover the information that is embedded within the object? Another question that we are trying to work through is what aspects of a 3D printed object make it more or less susceptible to having data be embedded inside of it. And we're trying to do some analysis to see if maybe the number of vertices or faces within the object allow for it to be have more entropy and have more or less data to be hidden. So what we're using to actually encode the image first is something called SteganoGAN. So it uses a generative adversarial network, GAN, that's what the GAN stands for, to encode an image. But first we had to re-implement this because it's a little bit old, so it had some dependencies that aren't available anymore. So our first task was to re-implement that, and that's still kind of work in progress. And then the data that we're using, we got access to an awesome data set called FabWave. And basically it's a 3D part repository that contains over 100,000 objects, and each object has an STL file, a JPEG, and a step file for that object. So which is perfect for what we need to be using it for. So we are trying to submit a paper by the end of the month to SCPS 2021, which is basically just a kind of a concept overview, and it kind of outlines what we want to develop in the future. Because later in the semester, we are going to be developing a second paper that builds on the first one and kind of implements this idea as we get more access to the ISIS building. So this is kind of the goal of what we are looking to achieve. So as you can see, you start with a cover image, which is basically an image of the object itself, and also message M, which is going to be any sort of data that you want to encode into the object. So you combine C and M, pass it through Steganogram, and it produces a steganographic image S which is basically the same. Physically, it looks like the same image as the original, but it actually includes the data that you had embedded in it originally. And then later, you have an STL file that lists the points of where the data is being located. And then you pass that into the printer, and it actually prints out the object with the data that you had embedded originally through the GAN or through Steganogram. And then finally, if someone wanted to, let's say, know where their part came from, they could use some post-processing tool to extract the data on their end. So some key takeaways, some lessons learned. So Dr. White let me and another graduate student that I was working with basically kind of form our own research question. We kind of came in there with a blank slate and were able to develop our own research question. And this was great because we had a lot of freedom, but also it was, I realized it was very challenging to get something that was concrete, a question that was concrete and interesting and hasn't been done already. But I think that we've finally landed on something that was good. Some challenges faced, learning curve. I think that a lot of other people have kind of mentioned this, but I also didn't have that much experience with the industry that I was kind of researching in. So a lot of the work that I was doing was a lot of background research and getting myself up to speed. And then finally, what went well, I made some new connections, met new people, and hopefully getting my first paper accepted. And then also I'm able to work in the lab next year. Also, I worked a little bit with Randy, who's going to be presenting next, over some bash command data generation, and I helped him out with that. So thank you.
All right, thanks so much. Randy, are you in a good position to start your presentation now?
Yeah, hold on, let me pull up the slides for a second.
Okay.
Okay. Make sure. Can you guys see the slides?
Yes, we can.
Is everything okay right here?
Yep, I'm seeing takeaways.
Okay, all right. Sorry about that. All right, from the beginning. Hello, everyone. My name is Randy Tran, and I've worked with Dr. Jules White, and also I've worked with Clayton on the Bash Code Risk assignment. So the research gap was basically current contents of Bash are currently handwritten, and the goal is to make it possible to randomly generate Bash commands using the computer. Since it's human readable, it's not computer readable. So the benefits of making Bash commands computer readable is to protect ourselves against the risk of our code. The main risk and the greatest risk of them all is human error, because humans are prone to create errors with their code. So the goals are to be able to compile Bash man page data into a CSV file to generate the Bash commands, and to generate random bash commands on a Docker image. Docker is used in order to mitigate potential unintended consequences of random commands and being able to run it on multiple different systems. Okay, there we go. So currently the progress is to be able to, currently the progress that we've made is we've done a data extract using Beautiful Soup, and we were able to scrap the bash's man page through an HTML code and extract relevant data such as command names, syntax, options, and keys, and to put them down and write them on our own text file. So the next step that we did was search each section of the text file, scanning through the text file and each command name separated by asterisks and stars, and the options that begin with the dash, which are different letters, for example, like -A, -B, and still it's not computer readable because of the descriptions that's next to it, which is just unnecessary information that the computer doesn't need. And the third step was to make a CSV out of it. So to make a CSV out of it, we parse down the text file to a CSV to easily navigate and interact with the data. So the CSV should have 3 columns: the command, syntax, and the option keys, which makes everything just laid out and cleaner. And then the fourth is to generate commands using the data from the CSV to generate random yet functional commands by adhering to each command's and syntax and options. This would be optimal to be able to generate the 15 most popular commands like ls, cat, and make directory. And the fifth step would be to gather the data, which is affirming the commands and demonstrating the system's functionality and compiling a list of commands to further demonstrate its functions and seeing if it is able to function to generate the commands and make it machine readable. Currently, it's not working. Okay, there we go. So this is the data. And so like, for example, this is the text file on the left, which is we have a list directory, the syntax, the list with the option in the file. So the keys are the keys that we use to for many parts of the list directories. And so -A, -all, almost all, and -B to escape. And the reason, and the next to it is descriptions, what we're trying to get rid of. That's what we're working on right now, because that's unnecessary information that we need. And on the right, that's what we've worked on. We've used a Beautiful Soup with Python, and we used a bash scrape to scrape HTML code off of a website to create a bash command data text and to create a bash command data CSV. And we also created a Gecko driver and a list text, which is like what we see on the left here, and a random command generator and a scrape that we've also created to make sure we have other working scrapes. So the key takeaways of what I've learned are that research requires asking questions, and there are no dumb questions. What I've learned is you don't know what you think you know, and I've actually had a lot of things that I needed to learn as I did this research. And the challenges faced is, like I said, the learning curve and adapting to the next challenge. I coming into this project, I had no idea what Bash was. I had no idea what Docker was, and I had to learn, on the fly and adapting to the next challenge. There were constantly challenges that I faced, especially with debugging and different things of that nature. And what went well? I developed a lot of skills in software engineering in general, and learning a lot about Bash and Docker, and collaborating with great people like Xiangwei Qiuchen and Dr. Jules White and Clayton. I really appreciate Clayton for helping me out. Without him, I'd probably be lost. And here's the repository. And yeah, that would be my research for the Bash risk assessment.
All right. Thank you so much, Randy and Clayton. So we are at the end of the presentation schedule. For those who have been watching, are there any questions for the interns about their presentations that you saw today? And I think we have couple minutes to take questions if anybody has those. Alrighty. If not, to all the interns who presented today, you guys did such a wonderful job. All of your presentations are really engaging, and I enjoyed learning more about what you've been working on this summer. So again, these interns who just presented today, many of them, their last day will be tomorrow. And it's been a real pleasure having you here this summer. So thank you to everyone who's watched these presentations. And if you have any questions for me or for the interns, feel free to reach out to me, and I can connect you to each other and pass on contact info and such. So, okay. Have a great afternoon, everybody. Thanks so much.